All right, sure. Yeah. So hello, everyone. My name is Anastasia Budko, and I'm from the Berkeley Lab. Oops. I'm from the Berkeley Lab. I'm part of the computer architecture group. My background is in classical architectures, microelectronics, HPC, computer science. So I've been I used to say I'm not a quantum person, but since I've been working with our quantum team for 10 years now, I don't think I'm allowed to say that anymore. So, but yeah, as I said, my background is on the classical side. So today I'm going to be talking about the quantum hardware stack, since that's most of the work that I've been involved in, although you probably know that at the Berkeley Lab we do have a variety of different topics related to quantum that are covered by other people in software and technologies and all sort of layers. But yeah, today I'm going to talk mostly about the control challenges and specifically for superconducting qubits. So, all right, a little bit of introduction, just a few slides. You've seen them before, I'm quite sure, but I have to start somewhere. So, yeah, so you know how quantum has become such a hot topic some time ago, and it's actually been around for a while. In theory, it's been developed for many decades, but you know, recently, a few decades ago, the classical community has become more aware and more, you know, interested in quantum. And you know, many people believe that that is coming from the fact that we no longer can deliver the continuing performance scaling through the you know, comfortable technologies like the regular transistors, and that kind of make us look into other technologies. And there are actually a lot of different varieties, and this is kind of the three. You know, there are many ways you can divide and categorize them, but this is something that we use in, you know, in our group, is those three axes. Is the bottom one is the new architectures and packaging. So that's the most well, not the easiest one, but in terms of, you know, how our manufacturers and you know what kind of tools we have is the easiest from this perspective. So just developing customized, you know, architectures, developing new chips, and you've seen all of that, all of the special purpose architectures. It's like it started with the GPUs, but now we have TPUs, we have different kind of special purpose chips. So that belongs here. And then we have new devices and materials. So it doesn't really change kind of the software stack, I think, but it does change the, you know, what is underneath, and that's, you know, different types of devices like TFATs, etc. And then there is the new models of computation, and that's where the quantum sits. There is also neuromorphic and analog and different kind of non-conventional computing techniques. So although quantum sits on this middle X, I do think that to be fair, to bring quantum to life and make it you know, practical, actually we do need progress to be made in all of the three axes. Although quantum is in the middle, we do still need to develop, as a community, we do need to develop new technologies for the control to develop on new architectures, I would say, to, you know, control the quantum. And then we do need to use new devices and materials for those new architectures, because of how quantum is actually also a different technology, right? So yeah, so that's my introduction. Again, there are different types of quantums, and the superconducting is just happened to be one of the most mature. It does keep changing. I'm not saying it's the best and will remain so, but it's just happened to be the most mature for now. And we do have this technology available at the Berkeley Lab, so that's where I've been working on for most of the time. I did try to include as many work as possible to my talk, but in general, I'll cover kind of two topics. The first one, it's a short-term quantum control solutions, which would include the custom architectures and also some FPGA-based solutions, and I'll talk about. Then I will talk about more of like a long-term quantum control solutions, and I will talk about the new technologies. And across like both of them, I will introduce some of the AI for quantum that we used in both of those topics. All right, so okay, so challenges in the control hardware, again, specifically for superconducting technology, and I'll specify why is this, you know, necessarily superconducting related. All right, so one of the inaccuracy, like one of the problem I saw back like 10 years ago, it's not that big of a deal now, but I do believe there's still this inaccuracy of terminology, where when people are saying quantum computer, they do imagine it to be like a single machine, while in practice what they usually mean is just a quantum processor. It does change, especially with HPC and quantum becoming such a hot topic. I see it in many conferences. A lot of people are talking about that, and then that brings attention to the fact that quantum computer is not actually just a quantum processor, but it's a very complex system. And all right, well, that's I was a little advertisement page, but well, Quantum Testbed is not active right now, but it was a project that at the Berkeley Lab that kind of tried to address the fact that the quantum computer is a a cross-disciplinary machine where we needed attention from obviously quantum physicists and material scientists who work on the quantum side, and then having computer scientists, engineers, and industry partners to address the classical side of that. And this is actually our setup. So as you can see, it's not just a chip, it's a very complex system. That's an actual photo of the testbed, where the superconducting chip, quantum chip, is actually located inside the dilution refrigerator, while the classical control is outside at the room temperature. And you can see all of those wires, blue wires, coming out of the room temperature control and going down to the fridge. And that is just a small part of the challenge on how to control those qubits. And just to clarify, the chip is not big. The chip is like just, I don't know, barely a dozen of qubits, and yet that's how much wiring you need to have to perform the quantum experiments. Not even the kind of a full scale quantum computation, but just like experimenting with algorithms and testing the qubits, etc. So in our setup, we had commercial partners. So we had Keysight and Zurich Instruments and some other, vendors who do specifically target the control hardware and control hardware for quantum. And we also did have our small team of engineers and scientists who have been developing the custom architectures on the FPGAs running in parallel. And on the course, over the course of 5 years, the conclusion was that it's actually less expensive to pay for labor. In California, you understand that's expensive. That's less expensive than to purchase it from the vendors, and you have the benefits of having full control over every single piece that is designed, every single unit of the control hardware stack and software, versus what you get from the vendors, where the quality of their hardware is comparable to designed by our engineers, but we don't get the same access. And that was a very, important piece for science to be done to have the full access. So eventually we spend much more time developing our in-house control stack, and it's an open source stack. We have Quasar that I developed, and then we have Cubic, which has been developed by some of my colleagues. Yeah. So, all right. So let me just quickly tell you what is the nature of this complexity of the quantum experiments, and specifically why the technology matters and what is specific to superconducting qubits. So this is an example of a very common kind of operation in quantum, which is part of error correction or some complex algorithms. Is when you have to do something that is called a mid-circuit measurement, where you're running the circuit, you applying your gates, and then you have to measure a particular qubit, and then depending on the state of this qubit, you're making a kind of a fork or a conditional branching in your algorithm, performing a dependency operations. So that being said, the problem here, especially for superconducting technology, is that the lifetime. Let me see. Okay, yeah, the lifetime of the qubit, was something that sometimes is referred to as a decoherence time, is how long can you perform different operations on the qubit before it collapses into a particular state. So the lifetime of superconducting qubits is relatively short. So on other technologies, they have different lifetimes, but superconducting is, I don't know what's the most recent one, but you cannot extend it very significantly. I think it's in the order of maybe a microsecond these days. But yeah, it's definitely not that much. And so that being said, that's how much time you have to perform the experiment. And then each of these blocks, which is the gate or the operation, is has its own time, which is usually measured by a pulse duration, and it's in the order of let's say 10 to 20 nanoseconds for a single qubit gate operation, a little bit longer for a 2 qubit gate operation, and then for the readout, it's even longer. So when you combine all of this information together, you realize that in order to perform as complex a circuit as possible, you need to deliver those pulses well, the pulses need to be like as short as possible, one, and they need to be delivered very quickly too. So, and the problem here is that when you have in this conditional branch, you involve your control hardware that needs to make an informative decision on like what is the next steps. So that's another example of the control stack, just a simplified version of the picture I showed with the cables. So what happens is that there's a room temperature control, there is DUCs in ADCs that send and receives the information. So the signal, travels through all of that, from the room temperature through many layers of, cool down layers of the dilution refrigerator, and then it reaches the QPU. So that's a non-zero time. And then inside the room temperature control, there is, time to perform the conditional branching. So all of that takes time. And when you perform an experiment on just one single qubit, that's totally feasible, and that's okay. When you scale the experiment to multiple qubits, that starts to become a problem. So, and that's where some of the work I've been focusing on, and one piece of this work was the quantum ISA. So again, just a slightly different representation of the control stack. So that's a very typical stack that this work, I wouldn't say this work is outdated, but I've done this work like 10 years ago. I started working on this 10 years ago, and back then this was the most common situation. It's well, the community moves fast, so it's no longer like this, but people were adopting this fast feedback loop, specifically for the reason I just told you. But that was the original setup, where you would have your software stack, usually on the user host machine, where you have an algorithm that is compiled to a circuit and then into a sequence of pulses, and that is done offline. And then you would upload your sequence of pulses through some interface to your classical control, and then the classical control will just play what has been loaded. And it kind of facilitates a lot of like development, and it's easy to implement and modify. Everything is one place, and it was fine for the NISQ experiments, but it obviously did create those long latencies. It has this setup has limited bandwidth and not that much of a flexibility or allowing this dynamic decision-making process, and doesn't scale well. So an alternative would be to put this kind of green box that says quantum control processor into your classical control layer, and allow this control processor to make informative decisions. So you can still compile your algorithm into a circuit, but then instead of compiling it into a sequence of pulses, like a predefined pulses or a predefined sequence, you compile it to some sort of assembly language that is supported by a quantum control processor, and then let the quantum control processor create a sequence of pulses dynamically, and then make an informative decision in case of the mid-circuit measurement experiment. So that allows to reduce the latency, because the processor sits kind of in between the user and quantum chip. It has the necessary functionality in place. It allows better scalability and can go beyond the NISQ experiments. So the problem is that it does require specialized solutions. It's obviously harder to implement and modify because it is a hardware piece, and it might require commercial support. So, so since our team's been, already doing custom designs, so it was not that much of a commercial support problem, but it definitely was not the easiest to implement and modify. So requires specialized solution. That's a research question. I did some research on the different ISAs. As you probably know, in classical architectures, there is a variety of ISAs, but there is like two categories, which is RISC and CISC. And RISC is more lightweight, so that's what I used for the quantum instruction set architecture. So in this paper that I point out here, I did some research on the different encodings, and it's very classical architecture paper because that's what we like to do. So what is the, how many, it's like how many bits you have per instruction? Is this like, it needs to be a vector instruction? Is this like how many bits you need to address a qubit, et cetera, et cetera. Those are all limiting factors at the end because that decides how many qubits you can address at the same time, et cetera, et cetera. So if you're interested in this topic, I'll just point you out to this paper. And I did have a different implementations. One was something that is called the ROC processor, and it's more like an isolated module that would just be a part of a RISC-V ecosystem. And RISC-V is very popular ISA. It's been designed in Berkeley and adopted for many different special purposes scenarios, and quantum is just one of them. But it's been a much easier solution in terms of the hardware implementation because the ecosystem is already there. You have compilers, you have software stacks, you have hardware implementations that you can just take and modify according to your needs. And yeah, so that work I believe is very relevant, and is still very it still is. So yeah, besides the research that we've done on the different ISA encoding techniques, we ended up implementing this ISA processor. Well, there's an ISA and then there's a processor implementation, right? So the processor implementation was part of our previous setup where we have a VC707 FPGA, and that FPGA was directly connected to the Berkeley Lab test bed with the qubits, and we were able to demonstrate the fast feedback. That's the actual pictures of the qubit state, and it was a successful example. And this is a part of the software stack. As I said, a lot of the software for RISC-V based ISAs already exist, so that you just need to write your extension, and that's what has been done. And this is just a sneak peek of like a C++, yeah, it's a C code for the programming purposes. And then we also run experiments to do the T1 measurement, just to show that, to demonstrate that it's not only running on simulations or something, but it's also can perform real measurements on real qubits. So yeah, so that's some of one piece of the work. Okay, yeah, one piece of the work that's been done on the control stack. All right, let's move on to a second example of the control hardware development, and that's this one will be about the QSD, which is the quantum state discriminator. So I'll bring here the same picture showed before that has this room temperature control, and that's a very simplified version of the architecture. But as you can see here, there's a processor core, and let's say it's the Quasar processor, for example. That's the core that makes decisions, right? That runs the instructions and generates the pulses for the gates. And then the state discriminator is another unit that takes the readout data that is coming as an INQ plane or the same picture as you saw just previously, like the blobs. This is the kind of how this information is usually visualized. And then those blobs need to be run through some sort of discrimination to determine the state. And there are different methods to do the state discrimination. I won't go into much details about them, but as you can imagine, they all vary in terms of accuracy, complexity, the outcome, fidelity, et cetera, et cetera. I think the easiest and the easiest state discrimination method is just the threshold line, where you just draw a line and everything that falls on one side is considered a 0. Everything that falls on the other side is considered 1. As you can imagine, if I go back here, yeah, sometimes you can draw the line pretty easily. Let's say here we draw it at 0 and get a relatively accurate count. And sometimes the blobs are too close or overlap even, and then it becomes harder, and then you need a more sophisticated algorithms to do the state discrimination. And I think recent work have been demonstrating the use of neural networks to do the best kind of state discrimination in terms of the accuracy and performance. So yeah, so this is the state of the art. Maybe not the most recent one, but quite recent still. I think I saw a couple of other works coming in 2025 and maybe even 2026. So yeah, so this table needs to be double checked, but it is still a relevant representation. So some of those work, they do the state discrimination real time, allow optimization, some not. Some are machine learning based, some allow to do the mid-circuit, some can do large scale or not large scale. So CubicML is a work from my colleagues at the Berkeley Lab. So I took it as a baseline for my work. So CubicML was designed as a neural network that kind of a custom neural network that sits on the FPGA. So just to give you, well, I don't have the right slide, but the fact that it's not large scale is because it does take the FPGA resources. And as I said, this part of the work is still kind of a near-term category because you can not scale it to up to like 1,000 qubits. It's not really efficient scaling. You can if you have unlimited money, I think, but it's expensive, and there is a question of synchronization at some point. So what I've been exploring is to using some other AI capability on the FPGAs. And for the sake of time, I'll just fly through those this background information. This is a one of the recent boards, which is a VCK190 board that has something that is called a Versal AI core series. This is, again, another example of special purpose architectures that's been designed by AMD Xilinx. And so you can use the FPGAs in different ways. You can use the programmable logic, and that's what this is what the CubicML team used. And you can use a deep learning processing unit. I'm not going to be talking about this one. It's not relevant to this work, but what I've been trying to use is the AI engine, which is a special purpose accelerator that sits next to the programmable logic on the board. So this AI engine is an array architecture. It has multiple tiles, I think they call it tiles, with specific core architecture and the memory. And inside each, you have a local memory and you have an ISA-based vector processor. So in my work, what I've done is that I took the neural network with those 3 layers. This is the neural network that the CubicML implemented on the programmable logic, and I dissected it and implemented it on top of the AI engine architecture. So one of the benefits of the AI engine is that it has the vector operation. So when it's useful, so when you compare the neural network that is relatively small, like this one, it's hard to see the benefit to implementing it on an AI engine, because it would, as something, it would still have some overhead performance, overhead time, and that would, reflect on the performance. And then what is interesting is that if you scale this network, or if you have multiple qubits, you have to control the overhead, becomes less and less relevant, and you kind of have a much better scaling. So that's been the main motivation for this work. And I do have some results on the running it on the FPGA. So another piece is that when you are running your architecture on the programmable logic, you have to be very cautious on the timings. You need to meet the timings. You cannot really run it at a very high frequency or very high clock rate, while the AI engine can run like at the gigahertz and even more. So that's another plus. So that being said, I compared. So the main initialization is what I'd say it's an overhead. This is something that remains constant, and then the kernel time is what is comparable to the CubicML. And the CubicML was, I think, 54 nanoseconds inference time, and the AI engine was 81 nanoseconds, which is still, it's a little slower, but it's still under 100 nanosecond, which was what the other related work was. So I claim it's a success, especially if this stays the same 80-ish nanosecond, even when you do the inference for multiple qubits. So, and that's just to show you how many resources been used. Again, that's been something that I wanted to do to explore the scalability. So as you can see, you can extend this to a much larger neural networks or supporting more qubits if you wish, because the resources were by no means used at the capacity. So yeah, I also measured some power consumption, not really relevant, but yeah, still an interesting metric to see, an interesting metric for my next topic about the next generation technologies. Because when you are at the room temperature, you don't worry about that much, but once you move your control hardware into the fridge, then the power consumption becomes a much larger topic. So, and I'm here coming to my last piece of talk, which is the low temperature control. And that's the same picture I showed you earlier. So now it's kind of a third iteration of the architecture, and the question is, can we take this classical control that we implemented on the FPGA, and can we move it to the low temperature environment? So can we avoid all of those blue cables and instead place it inside? In this case, we'll be able to reduce the latency further. We'll have a much faster feedback, and we can have an integrated scalability and go far beyond the NISC experiments. So the challenges would be the potential noise of these electronics. As you know, qubits are very sensitive. They don't like anything. We don't know what affects them sometimes, and putting some other electronics nearby could potentially harm the experiment. So need to be very careful. Then it does require new technologies, as I said, because we cannot just take a regular FPGA or a regular CMOS chip and put it into a millikelvin environment and hope that it works. No, we need to take a cryo FPGA or a cryo CMOS or other technology and test it in the in the millikelvin environment, or a low temperature 4K environment. And then even further, if you take some new technology, which is a non-CMOS family, you quickly realize that you need not only all of those experiments, you need to actually rethink all of your architecture styles because of all of the different properties that a new technology usually implies. So this is something that's been actively looked at for, I'd say, last 5-ish years. As I said, yes, there is a cryo CMOS. It's pretty popular in the current days. People are looking into cryo CMOS to be placed near qubits. And my theory is it's mostly because of the fact that it's still a CMOS. It means that a lot of the fabrication processors can be compatible with a regular CMOS, so the fabrication is a big deal. And a lot of tools exist for that, so it's just easier for deployment. However, it comes with I believe that the cryo-CMOS technology is not the optimal solution for that. It has, I think, unacceptable noise budget and power budget. It also does not allow us to do something that is a monolithic integration with the qubits. I know it's a far-fetched, but we're talking about future. So actually, for the low temperature technologies, there are quite a lot of different varieties besides the cryo-CMOS. And there is also something that is called RSFQ, which is rapid single flux quantum, or a QFP. And those are a variety of superconducting technology, the same technology that is used for qubits in my case. So the superconducting technology for classical computing, again, has been around for some time. it's not necessarily new. It's been developed in parallel or unrelated to quantum. And the reason why it's been so interesting is because it can run really fast. It can go up to I think 100 gigahertz, opposite to a few gigahertz in CMOS, and that was one of the potential benefit. So I will not go into details. I have just a few minutes left, but the implementing superconducting for classical comes with a lot of challenges, and there was a few programs in DOE and IARPA trying to address that. We've been working with the Super Tools program for a while, and know for a fact that it's not easy. This is work that's been done by my team. We had an LGRD project to do this, where we took the neural network that I just described in my previous chapter, and we took the RTL and we just tested it and implemented the same neural network, but using the different technologies like superconducting and also cryo-CMOS. So the kind of lesson learned from that is that it can be done. It can be much faster than the regular state-of-the-art. But as you can see here, the largest demonstration of superconducting chip is a multiplier that resulted in 20K Josephson junctions. It's a metric to show the area of a chip. And that's the maximum that is efficient. Then our implementation showed that it needs a 344K Josephson junction, which is just not practical. So what needed to be done is that when we used something that is called an biologically inspired data representation or unary representation to map the information, and we created a new library for all of those operations, and created a new functional units for the neural network. So we had to redesign the entire from the Josephson junction library to the unit, to the neural network unit, to kind of take into account all of the specific of the technology. And then this way we were able to create a representation of the neural network that was just a 3K Josephson junctions and was, still very fast, just a 4 nanosecond, and had a very little power consumption. So that's been a big success. And we are, I don't have time much to talk about that, but we have a Nature paper accepted, so it's coming soon. So if you're interested, please let me know. There's much more details about this work there. There's a lot more to what we've been doing, but this is the major 3 developments that I think might be interesting for you guys. So thank you for your attention, and I am all done with my talk now.
Thank you, Anastasia. Do we have questions for Anastasia? Amir? Go ahead.
Maybe a simple question. You still need to read the data out of, for the cryo CMOS or the superconducting work that you guys are doing for the controls. You still need to read the data and send it outside to some compute in room temperature to actually make use of the data that's being controlled. And you still need to take some input from external to actually tell the control electronics what to do, correct?
So if we are, where's my window? Sorry, if we are talking about the last piece, okay, so the last piece of work, when we have the state discriminator that is implemented using the superconducting technology, now we actually don't need to send the data to the room temperature. That's all processed in the low temperature environment. So that, which is a great benefit to compared to the room temperature. So, but in order to make it happen, you need to develop some other pieces to this, like to the control stack, which state discriminator is the main piece, but then there are some small side pieces that needs to be done, especially related to the memory technology, which is a very questionable piece for superconducting.
So just to be clear, the only piece that is happening in low temperature is the state discrimination, right? Not the actual like generating the pulses, etc.
So we do have some experimental work where we took a kind of a quasar-ish processor, and we did with the core, let's call it just a core, and we did run it through the same tools. So we can place a simplified version of that to the to the low temperature environment. So there's some challenges with that as well, but yeah, we do have some experiments to demonstrate that it's feasible.
Okay. And in that case, you do need some connection with the room temperature stuff, because it still need to get like the pulse table, for example, to execute.
Yeah, that's kind of a tricky question, and kind of we're still working on that. It's not easy to solve. We believe that you can get rid of the table if you implement it in a different way. Like there's a different ways to generate the pulses. If you're using superconducting technology as a pulse generator, you can generate them on flight instead of like getting the envelope from the memory, which is how it's done today. But again, it still needs to like more research and more kind of architectural work to be done to kind of safely state that it's 100% done. But I think it's totally feasible. It just needs more work.
Thank you.
So Jeff, I think you're next.
Yeah, thanks, Anastasia. This is really interesting and fascinating work, and I'm so glad to get to see sort of this level, because I don't normally get to play here. I sort of missed in the transition from early on. It looked like you were using a kickboard, and then now you're working with a custom RISC-V processor. Is that correct?
So Kick is a different. So Kick is designed by
Fermilab.
Fermilab, right? Kick is designed by Fermilab, and we have something that is called Cubic, which is designed by Berkelab. We're not competing.
No.
We're both open source projects. So Kick, I think Kick originally started as a control for a different technology, not superconducting qubits. So we kind of developed in parallel. And I did talk to Stefan and some of the people who were developing Kick back then. They've been interested in doing a RISC-V processor as part of their ecosystem as well. I don't know if they've done it or not, but yeah. So it's just it's similar, but just a little bit of different flavor to that. Yeah, so we have Cubic, which is just it has we went through a lot of like development cycles and also doing research. It's kind of you have to balance these things, but we do have like something is called as distributed processor as well. So there are different variations of that, but yeah, doesn't make sense. Yeah.
I actually worked on some tangential Kick stuff, so it's always nice to see like things cross-pollinate. The other questions that I had actually was really like using these tiles in the ML accelerator and sort of managing this complex set of fan outs with multiple control systems. How have you sort of approached that general system programming problem? Is this like a is there any unification on that, or is it just sort of working at each independent level and sort of stitching things together?
Yeah, I think it's the last one.
Okay.
It's very hard to unify this stuff, especially when you work with Xilinx tools.
Yeah.
Yeah, so it's been a work in progress. Yeah, it's we actually we didn't move that far in our experiments to kind of actually integrate everything together. And one of the reasons is that the VCK board, VCK190 board, has a different combination of like it doesn't have the same DUX and ADC setup as the ZCU board. And which with what we use for our current setup. And I think what we're waiting for is for AMD Xilinx to release. They think it's coming, or it's coming like in the coming year, or maybe next year. I don't remember the timeline, but they have the new board that is coming, which combines both GCU capabilities and VCK capabilities together to allow some better experiments for us. So they don't design it specifically for us, but it's just happened that this board has what we need combined. Because otherwise, if you have just two boards, you need to navigate all of the, like, sending the data from one board to another, which is like just crazy.
Yeah. Okay.
Mhm.
Thank you very much.
Sure.
Excellent. One last question from Josh.
Thanks, Thomas, and thank you so much, Anastasia. Fantastic talk. My question was quick. Do you have a pre-pub of your paper up, or do you know a timeline when it might be published?
For the last piece of work?
Yeah, for the work that you mentioned there. You mentioned that it's not in Nature quite yet. I just was curious if you had a pre-pub up on archive.
Let me double check that. We might have something on archive.
Okay,
Yes,
I can drop you an email too. Thank you so much,
yeah,
but fantastic talk. I
please do.
love the work.
Excellent. Thank you so much. Yeah, and I'm pretty sure I can just share that with you, given that it's already been accepted and we're just like finalizing, like processing the fees and stuff. Oh, okay. Nick just dropped. Well, this one that Nick just dropped is about the AI engine technology. That's the paper that will. This is not the Nature paper. That's another paper. But yeah, the other one was called a cryogenic hardware accelerator for quantum state discriminator at 4K. Let me see. That's I'll just put it here. We had an APS talk, but it doesn't have that much of the content. But yeah, please do send me an email, and I can get back to you with the paper.
Awesome. Thank you so much, and great talk again. Thanks.
Thank you so much,
you.
Anastasia. And I'm sorry for the snafu at the beginning, getting you stuck in the wrong room. So
No worries.
or wherever it was. So if you don't mind, could you send myself or Amir your slides, and we can, do you mind sharing those?
No, I don't mind. Yeah, that pretty much everything is open science, so I'm happy
Wonderful.
to share.
Thank you. Well, thank you again for your talk tonight, and really appreciate it.
Thank
Excellent
you.
talk.
Thank you guys for having me. Yeah. Have a good
Thank
rest
you.
of your day.